All right, guys. So, as you may have imagined, I don't feel like teaching today. I feel like being the cameraman, so he's teaching. We're going to talk about solar radiation pressure because Patrick has done this for almost a year now. This is what he's presenting is basically his master's thesis. It's also a conference paper he presented in Colorado a few months ago. 1 month, 2 months ago? February, yes. Probably becoming a journal paper. This is part of the syllabus. It's not just for fun. So this is stuff that you guys should know. So it's going to show what he has done, and in the process of doing that, another perturbation will be explained. What else do I want to tell you? I think you have also an example in MATLAB that you can discuss. So I have a reminder for next Friday for me to decide what to do with the grades, which means for the second test, which means if you find errors by then, fine. Otherwise, I will just move on. I will assume that there's nothing else to discuss. Okay. So next Friday, I'll see where we are, and I think I'll give you these and play with the camera.
All right.
All right.
All right. Is it working? Bars moving and all that? Okay. All right. So since we're on the topic of perturbed orbits, I suppose, we're moving away from just a simple two-body problem. I'm going to go ahead and lead the discussion here on solar radiation pressure. It's similar to the atmospheric drag that you guys went over a couple lectures ago, in that it's a non-gravitational perturbation. And I'll start off with a little review here of some of the important coordinate systems that we're going to be dealing with. So we're all familiar with the ECI. The principal axis reference frame or coordinate system is going to be an Earth-centered, Earth-fixed coordinate system. But instead of being aligned with the vernal equinox, the Greenwich meridian, it's going to be aligned with the Earth's principal axes, because we're going to be dealing with, also on top of the solar radiation pressure, we're going to talk about the C20 and C22 harmonics, the gravitational potential elements. So basically, when you squash the Earth from the equator and squash it from the side, so you get these bulges. Basically, you create new principal axes, and I'm going to make a coordinate system that align there. And it's going to be about 14 degrees west, I believe, of the Greenwich meridian. So, and then also we're going to be looking at the local vertical, local horizontal that we all went over not too long ago. So let's start off the equations of motion here. So once again, we of course have the acceleration from the gravity, and we're all familiar with that. We have perturbations from the sun, the moon, the gravity from the sun and the moon, and then I'm going to add this solar radiation pressure. And for a lot of these simulations that I'm going to go over today, and the topics that we're going to go over, I'm going to be dealing specifically with geostationary orbits, so semi-major axes of about 42,000 kilometers. So I'll go into basically a rundown of the gravitational perturbations. So starting off with the contributions from the Earth, we have the Keplerian model, or the two-body model, and then we have the contributions from the oblateness effects. So that's going to be modeled here in this potential function with the C22 and C20 elements. But you can see, if you were to make these 0 and assume a spherical Earth, like we have been, all this nonsense goes away. We have a potential function of negative mu over r, where mu is the gravitational constant from the Earth. And then if you plug it back into this equation, if you were to take it from ECI like we have been doing, all these omega terms go away, and you get basically negative mu over r cubed, which is what we expect, times r hat, or r rather. Anyway, so this reason why this equation looks so goofy is because it's resolved in the principal axis reference frame. So basically, if you do a transport theorem, you're going to get these extra terms here. And then when you add, of course, the C22 and C20 effects, you get these extra gravitational elements. So this is just the Earth. That's the whole point of all that. So that's the acceleration contribution from the Earth. And this is the third body perturbations from the Sun and the Moon. You do a Taylor series expansion, get rid of the higher order terms, and you can approximate the contribution from their gravitational effects on the satellite with that equation there. But what we're interested in today is going to be solar radiation pressure. So what is solar radiation pressure? Does anyone know what solar radiation pressure is, aside from what I've written here on the slide?
Is it just the photons hitting the spacecraft?
That's exactly what it is. Yeah. So you got sunlight from the sun, of course, and the photons from the sun exert a force on the surface of the satellite. And so you could think of the analogy of sailing. So you have wind blowing on a sail. You can push a ship around with that. In space, there's nothing. It's a vacuum, so to speak. So the sunlight actually exerts a force which we can manipulate. When we look at the equation, we can see ways we can manipulate the force exerted on the satellite and actually determine the magnitude, the effect of the sunlight's exposure on the satellite and how it perturbs the orbit. And once again, talking about geosatellites, since there's no atmospheric drag at geo, the SRP becomes very powerful, or very significant, rather. So here's the equation that we're going to be playing with, SRP. And it looks a little noisy, but we're going to clean it up here in a little bit. But just like the atmospheric drag perturbation, there's a lot that goes into it, and we have to understand how all these terms come into play and manipulate the satellite's motion. So at GEO, well, first of all, we want to know how the sunlight is affecting the satellite, and that's what the solar radiation pressure constant is. You can look at tables to determine the strength of the solar radiation pressure at various distances away from the sun. And you can scale it, I guess, with this equation. We're going to scale it with this term here. So AU, of course, is the astronomical unit. And that R circle dot, we've all seen that, I hope, by now. That's the shorthand for the sun. And then we have this angle theta, which is going to be the angle between the normal of the sail surface, or the satellite surface rather. So if we have a square satellite, or let's make it a cube. And say the sun is over here somewhere. Say that this surface is looking exactly at the sun. We have a surface normal direction pointing this way. This would be the surface. If you take the cross-sectional area of the satellite, that would be the area that we're looking at here. And the direction perpendicular to that cross-sectional area is going to be this n hat vector that we're dealing with here. And basically, the angle between this n hat vector and the sun position vector is going to be really important in determining the strength of the solar radiation pressure acceleration on the satellite. So we're going to add this term into our model and see how it manipulates the satellite's orbit. And let's go ahead and look at some MATLAB stuff.
The other terms, the epsilon and the
Which ones?
epsilon.
Oh, yeah. So, sorry. So epsilon here is going to be the reflectivity of the satellite. So for solar sails in particular, you want that to be, it's a coefficient from 0 to 1. So 1 being perfectly reflective, all the photons bounce right off. 0 being perfectly absorbative? What's the word? Anyway, it sucks in all the light. So basically what happens is the scatter from the light acts differently depending on this epsilon coefficient. And so we're going to assume a perfectly reflective satellite. So we get a certain desired behavior from the resulting SRP force, which I'm going to go over here in just a moment. But first I want to go over how the SRP, the solar radiation pressure, affects the motion of the sun, or the satellite. Okay, so first I'm going to remind you of what happens in a geo orbit. Just two-body, nothing fancy. All right. So this, I hope, is what we come to expect at a geostationary orbit, which is two-body model, perfectly circular around the Earth. And this is over the course, I think, of 1 day or 1 year. Yeah. Okay, this is a 1-year simulation. Okay. And here's the orbital elements, just to remind you all again. Am I saying right? Zero, control to zero.
Comment on the initiative. They're all constant, pretty much, right?
They should be constant.
Yeah, they are.
This, I'm hoping this is a really small drift, but this shouldn't be going down.
Well, but it's...
Some major axis?
Yeah, but look at the digits. It is, but maybe numerical.
Yeah, I'm hoping this is numerical. Anyway, so these should all pretty much be constant. Yeah, eccentricity should be about 0. So this is just numerical noise. So what I'm going to do now is add SRP, and we're going to see how this changes. So first, let's look at the actual orbit. All right. So what is the difference between this orbit and the one we just saw? Is there any obvious difference? Can anyone see any obvious difference? I'm getting a no right here. So no? So this red line here is going to be the original orbit, basically. That's the geobelt.
How are you using SRP?
Okay, yeah, right here we're just turning it on. We're just pointing the satellite at the sun at all times. We're getting all the SRP all the time when we can. So before we had basically an acceleration pointing always at the Earth. And so we had no noise going out of plane. Does anyone know why the satellite might be going above the equatorial plane now? Any idea at all? There's no J2, it's just a two-body and SRP.
Is the Earth and Sun not on the same plane as the satellite?
That's exactly it. So the Earth is going to, I think it's about 24 degrees off the, or the equatorial plane is tilted 24 degrees from the sun's, I guess, ecliptic plane.
Yep.
So as you orbit throughout the year, you're going to get points where you're, let's see if we can draw this out. If this is the sun, we have points, and it's going around the sun, okay? So say, I think it's fall and spring. It may be summer and winter, whatever it winds up being. You have points where the Earth is over here in the fall or spring, and then 6 months later it's over here.
I think it's the other way around.
Or whatever it winds up being. And you have this tilt of the Earth's equatorial plane. So basically, you can see how the sunlight's going to add accelerations, or at least a force out of plane, and we can see that here.
Nice question, right?
Ask questions, please do.
So you're pushing always away from the sun. I guess that's important to say.
Yes,
So you're
that's an important part to note, yeah.
always to the sun. So the force is always away from the sun. Whatever the sun is, you're pushing away from the sun.
Yes, because it's going to be pretty hard, and by that I mean impossible, to get SRP acting towards the sun. So here's our sun, here's our orbit, or the Earth's orbit around the sun. This is how sunlight acts. It goes away from the sun. So basically, as it impacts your satellite, or even the Earth, for that matter. It's pushing this way. It's not going to push that way. So yeah, that's an important part to note. It seems so obvious, I forgot to mention it. But yes, the SRP is always going to be acting away from the sun. But anyway, I thought this was pretty cool, so you could visualize the effect that SRP can have on an orbit, and why it's important that we model these perturbations, because you look at the two-body problem we just had, and the geo orbit looks pretty boring. It's going around in a circle, and we think, okay, cool, we're ready to rock, we're ready to make satellite orbits. We're astroscientists now. Well, no, we don't know anything about perturbations, and even this is inaccurate, because we're not even including the sun or the moon, but you can see the effect that sunlight has. This is just sunlight. This is always going to be there.
This is very exaggerated, right?
This is very exaggerated, but realistic. This is based on a satellite surface of about 1,200 meters squared. So very, very large, and it's weighing about 30 kilograms. So the air-to-mass ratio, I'm going to go over that in a moment, is very important. But this is a realistic satellite, but still exaggerated, and this is an orbit which is... It's plausible, and as you can see, it's very far off from the geo orbit. We're not adding any thrusters or anything, and the sun is just trashing this orbit. But
It seems like it comes back, it never really goes away.
yeah, it comes back about, let's see, where is it?
You have a start at the end, right?
The end point is right here. Let's see if I can zoom in on that for you guys.
This is a year?
This is 1 year, yeah. So...
Comes pretty close.
It's here. Does anyone see the X somewhere? It's over here somewhere.
I was going to make a comment, but I don't know if it will be on video.
What's it called?
If this is what the satellite will do, it's basically not only the orbit is trashed, it's going to collide with all the other geostationary satellites.
Yes.
Which is true. I mean,
Yeah, there's a bunch of other satellites, not even geostationary. If there's anything in between the geobelt and low Earth orbit satellites, this thing doesn't care. It's going crazy.
So is this standing out like for geostationary satellite in the Earth's shadow?
Yes, we're going to get into that too. There is an effect that the Earth's shadow and the Moon's shadow even have on the satellite, but it's a brief effect. It's something worth modeling in your model when you're actually doing precise satellite orbits. But for the sake of this conversation, you can almost treat it as being negligible. But yeah, there is some effect. If you could keep your satellite between the Earth and the Sun, you can diminish this SRP effect. But that's going to be a really expensive maneuver. But I'm going to show you one more cool thing we can do with SRP. So that's just keeping the satellite facing the sun all the time. But what if we were smart about how we applied the SRP? So if we tilted, say, the giant solar sail at perpendicular to the sunlight, so basically we're turning off the SRP. If we did that at key times in the orbit, we can get something cool like this. And basically, we're increasing the semi-major axis using only the sunlight. And if we're smart about it, we can keep it in the equatorial plane too. So this is just, I guess, a statement on what you can do with some of these natural perturbations. They don't always have to hinder your satellite orbits. You can use them to your advantage. So this is a completely free maneuver, no propellant at all, and we're able to raise the semi-major axis a couple thousand kilometers, I guess about 1,500 kilometers in 1 year with zero fuel, just the sunlight. So going back to what we were talking about before with the atmospheric drag and doing differential drag and satellite formation flying, here's one potential application of SRP use. Once again, another important reason why we should know about these perturbations. And as you can see here in these orbital element plots, the semi-major axis increases steadily, the eccentricity increases, we're keeping it in plane, we have no inclination, and circular orbits on the equatorial plane, you're going to get really no RAN and no argument of perigee, even though it's not exactly circular. But anyway, I'm going to go back to the PowerPoint now, and we got an idea of SRP. All right, so what we just saw was an example of solar sailing. So what is solar sailing? And it's basically, it's utilizing that SRP force to your advantage and controlling the satellite's orbit. With SRP, you get a virtually infinite delta V because you have an infinite fuel source. It's the sun. So that pops, we're good. And then you can make these non-Keplerian orbits that we've seen. So say we were talking about before, we have the geo belt, and that's on the equatorial plane. And we were talking about, well, why couldn't you get a satellite to stay above the geo belt? You know, why does it have to be on the equatorial plane? And we're talking about, well, you could, but if you had a constant thrust out of plane to keep the satellite there, it's going to be an expensive maneuver. Hypothetically, you could do it with the sun. If you had a very, very large solar sail, you could always apply a force out of plane, and you could stack these geobelts, one on top of one another. But that's still kind of unrealistic.
So you're saying like a cylinder of geos?
Absolutely. So if here's the Earth, and we're looking at the geobelt from the side, so the satellite's going around this way again. Let's make this bigger. So here's the Earth. Here's the orbit from the side view. We can use the sunlight if it's under here. Stack this thing. We have a geobelt up here, or down here potentially, if the sun were up here. And that's something we actually do with sun-synchronous orbits. You could find a sun-stationary orbit, and you can have satellites there potentially, but you can stack those stationary orbits using the sunlight a lot easier than you can with the Earth, because you're not restricted to being on the Earth's equatorial plane. But basically, yeah, that infinite delta V gives you some pretty cool options here in terms of the orbit. And of course, like I mentioned before, you get reduced fuel cost, more room on board your satellite for sensors because you're not dealing with propellant, or you don't need to deal with propellant if you don't want to. And because, once again, you're not restricted by your amount of fuel on board, you can actually have pretty long lifetime satellites, or long satellite duration missions that aren't dependent on fuel costs. But anyways, going back to that noisy equation for the SRP, there was a bunch of cosine thetas and epsilons and just noise. We can clean this equation up quite a bit. And we're going to look at basically reducing that equation down to this. It's a negative A naught times cosine squared theta n hat. And so how we get this equation is we can take this shadow function. This will be, we just ignore that. Don't worry about the Earth shadow on the satellite. Treat this as a constant. Treat this basically as 1, so that'd be a constant of 1. Assume your area to mass ratio of the satellite is constant, which for most applications it is. And assume that epsilon is 1. We're going to kill this term, is to make that 0. Brings this 2 out front, and you're just basically left with cosine theta n hat times cosine theta. You get this equation. So a lot cleaner. And with this, we can really get a good grasp of how the SRP affects the satellite's orbit. So I like this diagram a lot here. So this will actually explain how the SRP acts on the satellite depending on the orientation of the sail surface. And if we go here, so here's the direction of the sun. So you have incoming sunlight going this way at all times. If you have your sail perpendicular to the sun, you're going to get the largest magnitude of solar radiation pressure acting in the direction of the incoming sunlight. But say we wanted to direct our SRP force 45 degrees above this plane, or this way. We can do that, sure, but at a cost. Now your SRP, the resulting force is going to be diminished. The magnitude gets smaller, and as you get closer and closer to 90 degrees, you still get some force out of plane, but once you hit 90, you basically turn off SRP because the satellite sail surface normal is pointing this way, which means the sail is in line with the sun direction, so all the sunlight's basically, it's not doing this anymore. And we had a discussion earlier about the Gaussian variational parameters formulas. We can see how SRP affects the semi-major axis and the eccentricity. So up top here, I have the equations for the Gaussian variational parameters for these two orbital elements, where FR and FS are going to be the radial and transverse force components of the solar radiation pressure. This is just, we don't have to worry too much about this right now. Just know that with SRP in particular, it's going to be a function of the solar radiation pressure and the orientation of the sail. So I'm going to talk to you guys about control of a satellite's orbit using SRP. One of the cool things we could do with solar radiation pressure. So let's see here. Does anyone know what happens to a satellite's semi-major axis if we were to increase the velocity? What's that? It increases the semi-major axis? Yes. And why does it do that?
Faster. So if it's at, let's say it's at perigee,
Mm-hmm.
you're going faster at perigee, so the apogee will be farther.
Exactly. That's perfect. So you're increasing the satellite's orbital energy. You increase the semi-major axis. So then what would happen if you decrease the satellite's velocity? Probably decrease the semi-major axis. So we can do that with SRP. So if the sunlight is coming along this line here, and the satellite's orbiting this way, if we were to position the sail so we could capture some of this SRP during this half of the orbit, what's going to happen to the velocity vector? Is it going to go up or down? Up, yeah. That's what the picture says. That's what's going to happen. Increase the velocity, you increase the major axis. Conversely, if we were on this side of the orbit, we use the SRP. If we apply it to the satellite, we're going to slow it down. We're going to decrease the semi-major axis. And here's basically what I just said mathematically. And I'm going to post an optional homework assignment for you all if you want to play with this SRP to get a good idea of things you can do with it. This slide is going to be really useful for you because I might have you decrease the semi-major axis, and this will be how you do it. But anyway, let's see what we did. So once again, we have a satellite. The air-to-mass ratio is going to be 0.8 meters squared per kilogram. So just know that's the A to M ratio that we're using. And with that ratio, that particular ratio, we can raise or decrease the semi-major axis 1,500 kilometers in 1 year. This is interesting. So looking at just the orange, since we can see the orange is decreasing the semi-major axis. Actually, don't worry about that. We're increasing the semi-major axis throughout a 1 year orbit. The entire time, we're increasing the semi-major axis. Why would this eccentricity go all the way up and then back down to 0 in 1 year? Does anyone have any idea why that would happen?
Is this with constant radiation always?
This is constant radiation. So why would the eccentricity go up to some max value and then drop back down to 0?
If you're increasing it while you're on one half,
Mm-hmm.
you're increasing it on the other half, so if we cancel out.
Exactly. That's exactly it. So you do have this natural reduction of eccentricity, or stabilization of eccentricity over a 1 year period. Even if we went back to that that plot I had before with the really cool out-of-plane orbit, the final position of the satellite was almost back on the equator. And it was, the eccentricity was pretty much zero again. It was back to a circular orbit. And then...
Can you sketch on the board the case where you see that you're pushing in one direction and back?
Yes.
Alpha year?
So, here's a picture what we can draw to help visualize this eccentricity effect. So here's our sun, and then here's the Earth's orbit around the sun. Say we start off right here. This is our Earth. And here is our circular orbit. We're going to push right here, which is going to blow the semi-major axis this way. Right? So we're increasing the speed here on this part of the orbit, and so we're going to get a larger radius on this half, so to speak. So we're making the orbit more eccentric. Eccentricity rises. We go here. Now, say we kept this orbit. We have this orbit now. But now we're pushing and we're increasing the velocity on this half of the orbit. We're going to start to blow it out this way. So let's go here. We have something that looks like this now. This is the part we're interested in. Increase the velocity here. Blow this out. What do we have? Increase here. Blow this out. Anyway, when you come back here, you have a new circular orbit, basically, because of that net change in the semi-major axis.
Are you only using the sail for half the orbit?
Yes. So this is always pushing to make the velocity increase. Same concept if we were to make the velocity decrease, except we would shorten these radii, but it would still, so you'd go from here to here, basically. But that's a just completely conceptual idea of what's happening. It's not that black and white, but this will help get the point across. This is how we're increasing the semi-major axis and increasing the eccentricity and then subsequently decreasing the eccentricity. Does that make sense? Awesome. Okay, so I'm going to talk a little bit, and a very little bit, about a Lyapunov controller. And I don't really care if you know what a Lyapunov controller is. But the point I want to make is we introduced these Gaussian variation of parameters formulas, and you might be asking, who cares? Or how do we care? What does that mean to us? And how can we use that? Because I know you guys can understand this geometric approach of how to change the semi-major axis. That makes sense. We can visualize it. But how do we utilize something like a dot, dAdt, dEdt? And here's an example right here. We can, part of the Lyapunov function is basically you can control the dynamics of a satellite if you know how the dynamics evolve in time and how its derivative evolves in time. So if we have this a dot, that's the derivative of the semi-major axis. If we can manipulate this a dot, keep it negative or positive, depending on what we want to do, we can use math, just math, to figure out ways to control a satellite. And as a result of using math, we can optimize this behavior instead of just pushing blindly with the velocity, which is something we can visualize, and we think, yeah, that'll work. Why not orient it with the satellite's velocity? Math tells us there's a better way with that a dot equation, and we can increase the semi-major axis 500 kilometers more with the exact same satellite, and decrease it 500 kilometers more with the exact same satellite, using that a dot equation, and just keeping that a dot negative. So just looking at how those terms behave with one another and doing what we can to make that A dot negative in something we call the Lyapunov controller, which some of you may be diving into later. But the point is, these Gaussian variational parameters expressions are very powerful, and with them you can get really good results. Very good. All right. Eccentricity, it's also an orbital parameter we can control geometrically or with these GVEs, or these, I call them GVOPs in this slide, the Gaussian Variational Parameters formulas. But let's look at a way to increase or decrease the eccentricity. So let's look at this plot one more time. And say we have this retirement threshold here. It's 300 kilometers above the geobelt. And this isn't a real-world example. We want to deorbit a satellite from the geobelt past this threshold, okay? Say we want to do that with SRP. So this plot shows that, yeah, we can do that with SRP. And we'd probably want to let the satellite go around 150 days based on this plot, because you don't want the perigee to have it cross back down below this graveyard threshold. But what if we wanted to speed that up for some reason? Because we can. How would we do that? With SRP, basically. We want to reduce this eccentricity, say, at this point, or this point, instead of waiting all the way until 180 days for the natural decrease in the eccentricity. We can look at another geometrical approach with SRP. And basically, this one's a little more involved. It's difficult to explain quickly, but I'm going to try. Let's look at this. So we're all familiar with this equation, right? This is always going to be true for any two-body problem. The sun, the moon, the Earth. You want a circular orbit, there's a circular velocity, and it's that. So what if we try to get the satellite, the velocity, to match this magnitude, a known magnitude, a known semi-major axis? So, like I said before, we want to raise the semi-major axis 300 kilometers. So say we pick 350 kilometers. So we can target 350 with that semi-major axis control that we just saw. But now we want to reduce the eccentricity. So we can now say, look at the velocity of the satellite throughout various times in the orbit, and try to drive that velocity towards this v-circular velocity. And we just saw we have ways to increase and decrease the velocity of the satellite during various parts of the satellite's orbit. So what if we just did it intelligently until the orbital velocity is equal to that circular velocity? Basically using that mentality, and here's how you would implement it mathematically, which you guys might care about later. This proves that, once again, using these perturbations, solar radiation pressure, you can decrease the satellite's eccentricity using solar radiation pressure. Granted, the time is not that great, but this is preliminary. It gets better. So just keep in mind that we can control the eccentricity. And once again, if we use the Gaussian variational parameters formulas for the change in eccentricity and time, we can do it more intelligently and get different kind of results. So if we were to compare this to this, you can see that if you look at this eccentricity plot in the bottom left, it doesn't decrease until about 180 days, I guess. Does that look right? But here, we get almost an immediate decrease in the eccentricity a little after 100 days. But we approach some limit. But if we're really, really smart, we can combine control methods. And basically, here's the point. This is what I want to get to. Using solar radiation pressure, eventually, yeah, we can drive this eccentricity down, make it a circular orbit, and we still maintain a desired semi-major axis above our graveyard threshold. And this is all using a natural perturbation force in the environment. We use zero propellant. We're just manipulating physics. And yeah, these physics come from these non-two-body perturbations that, for some reason, isn't in the back of your textbook. Oh wait, it's in version 3, right?
Yeah.
Third edition. Okay, so you guys you have this. All right. So going back to what Dr. Bevilacqua was saying at the end of that last lecture, or whichever lecture it was, about how you do all this and you're just playing with two-body orbits, but who cares really, because there's so much more going on. You really have to know how these perturbations affect the orbit. And here's basically this whole talk was just an example of how you can use these perturbations to do cool things with the satellite orbit.
Can you explain how maybe one of those Gauss variational equations real quick, how you use them?
How I use them?
Yeah. Do you have a slide of that?
I got rid of it because I wanted to.
Okay.
You talking about the geometric approach with the?
Yeah. Maybe you can do it from here on the board. I don't know. That makes sense.
1 second. So the question was, how do we utilize the Gaussian variation of parameters formulas? So I'm going to pull up another PowerPoint really quickly and show you all basically how we use that formula when it comes into play, when it's important. Okay, so let's look at this.
It's very high level.
So we saw the slide before, so I'm going to start breaking it down a little more in depth for you all. Don't worry so much if you can follow everything I'm saying. Just try to keep your eye on the point of what I'm saying, and we can see how we can use these Gaussian variation of parameters formulas to our benefit. So we have the ADT. Okay. A gamma R plus B gamma S. So here's the basic breakdown of the Gaussian variation of parameters formula. In fact, let's do it right. This is a more inclusive expression here. R plus B plus C. Okay, so going back to that RSW. Going back to that RSW coordinate system I was talking about, we can break down the force components into their. Basically, we can break the force down into its components in the R and S and W directions, and the local vertical, local tangential, or local horizontal coordinate system. So say we have those force components. I'm going to call them gamma R, gamma S, gamma W. Real generic. So here's SRP. Acceleration due to the solar radiation pressure. I'm going to put it in the vector. R, S, W. Okay? This is just the force components. Here's the magnitude. And then you have these parameters here, A, B, and C. In this case, we're not dealing with W because the ADT doesn't have a force component out of plane, or any out of plane components that affect the ADT. So we have an A, we have a B, we don't have a C. So A is going to be A squared E sine F over H. B is going to be this. In this PowerPoint, I'm putting it in a zeta vector. That's what that little squiggly line is. So I'm breaking this equation down into basically a dot product of two vectors. Is that kind of clear right now? Is everyone following so far? Right here, how we go from here to here. And if I were to define these two vectors, so if I were to take the dot product of these two vectors, you're going to get that exactly. But you know, changing some of the variables, I can redraw this in that form at the bottom. Anyway, the point is, I could take these two vectors, get really smart with them, and create a new basis. In this basis, the x-hat direction is pointing towards the sun. I define a y-hat basis that's basically this zeta vector, its projection on the xy or the equatorial plane. And then I complete the basis with this cross product. And then I get some angles basically. When I do this and I were to put these vectors, say the n-hat vector, which again is the sail surface normal direction, if I were to project it in this basis, I get these three angles. And with these three angles now, since I rewrote the equation like so, I can define an n-hat based on these angles that'll give me a desired behavior. Oh, cool.
You don't need to go into these.
But, okay.
That's the point, is you maximize the dot product or minimize the dot product.
Yeah. I'm going to go back to... Okay, we're going to go back here. So anyway, the point of all that fun stuff was I get some dAdt value from here, and with all those angles and the orientation of the satellite, I can make this incredibly negative or incredibly positive at any instantaneous time in the orbit based on that satellite's orientation. I plug that into this equation here, which is important for satellite control. I make this equation negative all the time. I get a desired behavior. Usually that equation is going to be some error function, and in controls you want the error to be 0. So if I make this negative, it's always driving the error down to 0. And that's basically the point. A really rough overview of how we can use the Gaussian variation parameters formulas to our benefit. Real quick though, I want to talk to you guys. I got 3 minutes. Okay. I'm going to talk to you guys about a simulation that is... What is this? What's going on here? Wrong slide. Okay. A simulation that we ran where we basically take one of NASA or a satellite modeled after one of NASA's solar sails. This is a real solar sail. This solar sail is 30 meters by 30 meters. Enormous sail. Never made it to space, unfortunately. It's just sitting in Ohio somewhere. But basically, we take some parameters based on that sail. So we're going to have a satellite mass of 30 kilograms, the 28 by 28 meter sail, and basically you get this air to mass ratio, which, if you know anything about solar radiation pressure, this is very large. And this is what our simulations have been based off of before. So all the control and all the changes in these the orbital elements that we were able to get before, they're going to be a lot better now, because we just increased the order of magnitude and then basically doubled it. And with that, we could do some interesting things. Like, for instance, a lot of these simulations, you saw what's happening here? Yeah. Oh well. I'll just look at this plot. You saw we got a lot of noise outside of the orbital plane. With a big enough solar sail, you can dampen that noise, basically the same way we dampen the velocity. You move the satellite sail in such a way that the resulting acceleration opposes the out-of-plane motion when you can. And you do that here mathematically. Yeah. And here's our simulation based on that sail I was just talking about. So the idea was to take a 1,000 kilogram piece of space debris from the geobelt, deorbit it, so raise it past that graveyard threshold I was talking about, release it, so we release it after about 220 days, and then let's bring this sail back down to the geobelt so we could do this maneuver over and over and over again. So let's clean up the geobelt. We're basically, we're space janitors. We want to get all the trash out of the geobelt. So this simulation basically proves that with SRP completely free, no propellant, we can hypothetically raise the satellite's orbit, release it, bring our TOSAT back down to the geobelt, hopefully rendezvousing with our next piece of space debris, and then repeat this maneuver over and over and over again for free. Yeah.
So
that's it.
We're going to post your software?
So yeah, I'm going to post those MATLAB scripts that I just showed you. I'll post them online. I'll work up some little exercises for you all if you want to play with the SRP.
Can you post the PowerPoint too?
And I'll post the PowerPoint as well. All right. Thank you all.